Hi guys, welcome to another session on mechanics of solids. We'll be discussing the shear force diagram and bending moment diagram. So here we have got question number 6.311 from 6.31 from HIbbeler R textbook mechanics of solid. So here as you can see the question is as follows. We have got a um, beam which can slide freely along the vertical guide at A, okay, with the supports over here. This is the vertical guide, and it doesn't support any vertical force. Draw the shear and bending moment diagram for the beam. Okay, so I'll just read it again. The support at A allows the beam to freely slide along the vertical guide so that it cannot support a vertical force. Okay, so they have mentioned that there is no vertical force uh, at the sliding joint A. Okay, so let's draw a simple free body diagram. So here it will be RB since it is a roller support. Then we have got uniform load acting on the beam. Okay, and here it says that there is no vertical load. Okay, so what else will it be there? So even if there is any horizontal, both of them will be cancelling each other and there won't be any net moment or net load acting about it. Okay, so let's consider um, so in order let's just consider there is a moment acting. Okay, so we don't know the direction of moment. Let's take this is the direction, ma. So this is the free body diagram. So since it is a uniformly acting load, we can assume that this particular load is acting at the center. Okay, L by 2. This is L. So this is acting at L by 2. Okay, and the moment is MA at A. Okay, and this is B. It would be better to write this A outside. Okay, A and B. And this is RB. Okay, and what will be the concentrated load? W into L, because W is Newton per meter, and W is the load density. Okay, sorry, load intensity. So load intensity into the length upon it which is acting. So W into L and acting upon the center. Okay, that is clear. So let us um, use the free body diagram and the equilibrium equations. Okay, let's do the moment equilibrium. Hmm? Okay, first let's do the force equilibrium. Sigma Fy equal to 0, thereby we get Rb is equal to Wl. Okay, we got that unknown. What about sigma m about a is equal to, it has to be 0. Okay, so ma is let's say we are considering counterclockwise to be positive. Okay, so wl minus wl into L by 2 plus RB into L. Okay, and what about A? At A it is clockwise now. Okay, so minus MA equal to 0. So MA is equal to RBL minus WL square by 2. That is equal to WL square minus WL square by 2. I just substituted this over here. Okay, that is WL square by 2. So that is ML, sorry, MA. So we got MA. We have to go back to the original configuration, loading configuration. Okay, so this was the original loading configuration where where we had a uniformly distributed load and the MB, that was WL square by 2. Okay, and I'm taking X distance. Okay, I'm using a cross section XX. Okay, from the end A. This is B. Fine. So let us, what do we do is, let us make a section XX and find what is Vxx. Okay. So at X distance from A, we have got W into X. Hmm? Isn't it? There is nothing else. No other shear forces. Okay. And at x is equal to 0, Vxx is equal to 0. At x is equal to L, Vxx is equal to L. Sorry, WL. What about the what about the sign? The sign will be, see, here the RB is in upward direction. Okay, so that is a negative WL and it is positive. Okay, so even if you draw it in the other direction, it won't matter, but the sign convention matters. I mean, you have to define how you are defining the sign convention. So this is negative, okay, shear force, huh? And this is positive shear force, huh? So this is my sign convention, what I have used here. That's why, um, so here since the RB is upward acting at B, so I have got negative WL, okay. Then the forces are acting in downward direction, that's why it is positive and becoming 0. Okay, I hope that is clear to you. So even if you take this section, uh, here the section, okay, XX, huh? Then the forces are acting in this direction, right? The effective shear force Vxx, huh, is acting at this direction, and this is point B and this is RB. Okay, so this Vxx is equal to Wx. What about this direction? Just relate this particular block with this block. This block. So you can see that Vxx is negative direction on the left hand side. And RB is here, as you can see here. So that's why this Vxx is equal to minus Wx. Okay. I hope that is clear to you. Next, we have got um, the moment diagram to be drawn. So in order to draw the moment uh, diagram, we have to take xx as usual, mxx is equal to, so either take the left or the right side of this particular cross section. Okay, so the moments acting on the left or the right side. So here, similar to shear force, we took only the left section, huh? So it was, this was, okay, okay, W, this is A, okay, so this was XX. I hope that is clear to you. So we took the left or the right? We took the left, that's why we got this particular minus WXS. So even if you take consider here also, you will get similar stuff. Nothing to worry. So here I have taken the MXX and let's say MB is acting in the, take the left side. Okay, so see the left side, it is a sagging moment. Okay, so we take the sagging moment as positive. And what about the moment due to the distributed load? That is W into X, that is the load, and it is acting at X by 2. This is X, 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 X. W is acting, okay, at a, it's acting at X by 2, right? If you reduce it to a unit compressive, so not unit, concentrated load, so you get WL square by 2 minus WX square by 2, that is equal to W by 2 into L square minus X square. Okay, thereby you can draw this particular moment diagram like this. Okay, X is equal to 0, WL square is equal to 0. This is X. Here it is X. Okay, so this is the shear force diagram. This is the bending moment diagram. Okay, thank you.